Okay. Only 13 members came up to now. Please all of you connect to your audio. Most of them have not connected to your audio.
मैं कथु बाजी हमें.
Okay, good afternoon all of you.
Good afternoon, sir.
Good afternoon. Just I am making all of you mute. Shall I start the session? Why only 13 members? Okay, good afternoon all of you. In the last class, we have discussed about how the transistor is going to act as an amplifier, right? That is how the output voltage will increase when you are changing the input voltage. We have discussed this one. Right? So whenever there is a change in the input voltage, then there will be large change in the output voltage. So we have used for this one as an NPN transistor, and also that we have used for a common base configuration, right? So to find out the voltage gain, we have a formula that change in output voltage divided by change in input voltage. So whenever you are applying some input signal to the input voltage, okay, why the participants? Just give me 1 minute. I will keep in your group that join immediately. Okay, clear, right? So in the yesterday's session, we have discussed about this concept, how we got a voltage gain and how the output voltage is so much high compared to the input, compared to the change in the input voltage, and how we are going to get the high intensity of sound if you are using, if you are taking example of a speaker. Okay. So the same, after completion of this concept, let us discuss about the three important configurations. Okay, so we have three important configurations. The first configuration is the common base configuration. Second one is common emitter, and third one is common collector configuration. So we have these three different configurations, right? So common base, common emitter, and common collector. Common base, how we are going to make it as all this as a common. If I want to identify which circuit is a common base, this base is a common for both input and output circuit. If you see the circuit here on the left hand side, we have input here, we also have output, but this base is common for input as well as output. Okay, for that reason we are going to call it as a common, and obviously it will be get grounded. Okay, so this is called as common base configuration. Okay, so in the tomorrow's session we'll try to discuss about common emitter, where it is also a common for input and output, obviously the common collector also. So let us try to discuss about common base configuration. Okay, in this one we need to discuss about the input and output characteristics of the common base. So just we are assuming one NPN transistor again. Okay, this is an NP transistor. So this is actually an emitter, this is a base, and this is a collector. So this is nothing but an input side, and this is nothing but output side. Okay, so this is an input side of a transistor, and this is an output side of a transistor, and this is NPN transistor. The working principle of NPN as well as PNP transistor we have already discussed in the last sessions, right? So now if I move to the applied voltage, because usually for every configuration we will get the three important regions. Okay, so we'll have the three regions. One region is an active region, as we already know. Okay, obviously we have 4 regions, but we are going to discuss mainly about 3 regions. That is active region, okay, saturation region, and cutoff region. So we have these 3, that is active region, saturation region, and the cutoff region. So based on, for every configuration we need to discuss about how it is going to act for active region, saturation region, as well as a cutoff region. Okay. So first of all, if for a common base configuration, we will try to analyze for an active region. How we could able to make the transistor to be as an active? We need to make it as active by making the emitter base junction as a forward bias, by considering the emitter base junction as a forward bias and collector base junction as reverse bias. Therefore, what happens? This transistor, NPN transistor, is going to work as an active region. That means the main application of making the transistor to work as an active region is nothing but to work as amplifier. So the main application of a BJT is nothing but to work as an amplifier itself. So let us try to discuss the same thing here. What I have done to make the transistor to be operated in an active region, I have made the emitter base junction as a forward bias and collector base junction as a reverse bias. So the voltage what I'm applying at the emitter base junction, at the emitter side is called as BEE emitter voltage. At the collector side is called as a BCC collector voltage. Yeah. So now what happens? There will be a flow of current whenever you have connected. You made the emitter base junction as a forward bias and collector base junction as a reverse bias. There will be also current will flow in all the junctions. That is all the terminals. We are going to call this current as an emitter current, which because it is an NPN transistor, therefore the current flow will be always from base to emitter. So see, this is a current flow direction. So emitter current is flowing like this, and base current and collector current. So this emitter current is nothing but a summation of collector current and the base current, which you already know, which we have already discussed. So what is this VBE? So VBE is the voltage difference between the base and the emitter. That is, audio is not clear. I have switched off my fan. Okay, just wait. Is it clear now? I think it is clear now. Just I'm continuing. So now what happens? See, this emitter current is nothing but a summation of the collector current and the base current. And what is these two voltages? Okay, what are these two voltages? Base emitter voltage. Base emitter voltage is the voltage drop between the base voltage and the emitter voltage. And this is also a voltage difference between the collector. We are going to call it as base emitter voltage and collector base voltage. So now what we need to do, we need to draw the input characteristics and output characteristics of collector base configuration. Just I'm repeating again, just we took one NPN transistor, what we have done already in the previous sessions. And for that NPN transistor, we are making the transistor to be operated in an active region. For that reason, we made emitter base junction as a forward bias and collector base junction as reverse bias. So therefore, there will be a current flow through the junctions. That is, the current flow is called as an emitter current. Through the collector is called as a collector current. Through the base is called as a base current. So this emitter current is nothing but a summation of collector current and base current. So we also have a two voltage drops. One voltage drop is between base and emitter called as a VBE, and one voltage drop between the collector and base is called as a VCB. Now I want to draw the input characteristics. Now our job is we need to draw the input characteristics. In order to draw the input characteristics means we need to have one x-axis and one y-axis terminals, right? What we need to apply is, if you don't want to draw the characteristics, we need to give x-axis and y-axis. So here, what are the characteristics means we need to draw the characteristics between the voltage and current. So this is actually an input side. So what is the voltage? The voltage is VBE is the input voltage and IE is the input current. So we need to draw the input characteristics between VBE and IE. Okay, that is, we need to draw the input characteristics for a common base configuration between the base emitter voltage and the emitter current. So y-axis we are indicating with an emitter current, x-axis we are indicating with a base emitter voltage. So considering the collector base voltage as a constant. Okay, when you're drawing the input characteristics, you need to consider the collector base voltage as a constant. So similarly, after drawing the input characteristics, we should also draw the output characteristics. So what are the output characteristics here? Output characteristics for nothing but again, it should be a voltage comma current. So what voltage we have here? The voltage, output voltage is VCB, collector base voltage, and the output current is collector current IC. So we need to draw the collector base voltage as in the x-axis, and in the y-axis we need to draw the collector current, considering the emitter current as a constant. In this one, we need to consider VCB as a constant And in this one, we need to consider emitter current as a constant. Okay. So based on this one, we need to draw the input characteristics. Based on this one, we are going to draw the output characteristics. Okay. Let us see how we are going to draw the characteristics. See, if you see perfectly here, so this is actually input characteristics. Only 24 members came. I have instructed in the yesterday itself that all of you must and should attend. I have given the rule numbers also. Okay, sorry. So now input characteristics, which I have already told, we are going to draw the input characteristics between the input voltage, that is base emitter voltage, and also the input current, emitter current, right? So if you see, this is actually the same characteristics just like a PN junction diode. If you observe clearly, these are the same characteristics just like a PN junction diode for a forward bias condition. Why these are repeating means this is the same thing, because for an NPN transistor, this is actually for a forward bias condition, right? So this, from this point to this point, this is just like a forward bias condition of a PN junction diode. For that reason, it is, you are getting the same characteristics for the input. Okay, just like a forward characteristics of a PN junction diode. So at VCB, that is, we have considered VCB as a constant. If you are varying the VCB also, there will be change in the emitter current. If whenever you are increasing the collector base voltage, then therefore the emitter current is also going to get increased. You see, and what is actually the forward bias characteristics of a PN junction diode? Whenever it is crossing, whenever whatever the voltage you are applying at the input side, whenever it is crossing the depletion layer voltage or a barrier voltage, then the current will start increasing, right? So in this one, only one condition is about the VCB operation. See, so what this VCB is at the output side voltage, right? VCB is output side voltage. So when it is zero, when it is moving from 0 volts to 5 volts, that is when the voltage is increasing. Assume that when the voltage is increasing, emitter current is also increasing. That is, when the voltage is increasing, that is, you are increasing this voltage. You are increasing this voltage means you are increasing the reverse voltage. You are not increasing the forward voltage. Please keep this point in your mind, because it is working under the reverse bias condition. You are increasing the reverse bias voltage. So whenever you are increasing the reverse bias voltage, this depletion layer width will increase, which makes the base junction width as narrow. So when this collector layer width is increasing, which makes this base junction as so much narrow, therefore the emitter current will increase. So which increases the emitter current. Okay, you can see, you can observe this one here. So when you're moving to 0 volts to 5 volts, okay, when you're moving from 0 volts to 5 volts and 5 volts to 10 volts, the voltage, that is the current, is started increasing. Okay, it is increasing gradually. Okay, it is coming from the left hand side of the axis. If it is moving towards the y-axis, if you see, from this is a first position, this is a second position, and this is a third position. It is moving to the left hand side. It is not moving to the right hand side, because it is not. It is controlling the VBE voltage. Okay, see here. If this is at one point, if I'm assuming this as a 1 point, okay, this is 1 point. It is moving to this point. It is moving to this point. That is, the VBE voltage is decreasing. Why the VBE voltage is decreasing? Why the VBE voltage is decreasing? Because the base junction is getting so much narrow. So when the base junction is getting so much narrow, what happens? Usually the VBE voltage will get decreased. So for that reason, you will get here VBE decreasing when VCB is increasing. VB is decreasing, but emitter current is increasing. You can see here, we have these 3 points. You perfectly see here. Sorry. Current is increasing, right? For condition 1, for condition 2, and for condition 3. So these are actually the input characteristics. If you want to find out The input characteristics means just these are the characteristics which it is drawn between the input voltage VBE and the input current IE, considering VCB as a constant. But in this case, when the VCB is increasing, when the reverse voltage is increasing, the emitter current is also increasing, but the input voltage or the VB voltage is decreasing. So we could also find out the resistance. We are going to call that this resistance as input resistance. If you want to find out, means you can also able to find out the input resistance. Input resistance is change in the VBE divided by change in emitter current. Okay, change in the voltage at the input side divided by the change in emitter current will give you the input resistance. Yeah. Okay. So these are actually the input characteristics of a common base configuration. Okay. So now we'll try to discuss about the output characteristics. What actually output characteristics? Characteristics are the characteristics which are drawn between the collector base voltage and the collector current, considering the emitter current as a constant. If you see here, so these are the output characteristics. Okay, these are the output characteristics. Just give me 1 second. Okay, these are the output characteristics which it is going to drawn between VCB and IC. Okay, which is going to drawn between VCB and IC. VCB is output voltage, IC is the output current. So in this one we have a 3 regions. So you can consider, we could also discuss about 3 regions. This region is called as, this region we are going to call it as region. I think the font size is more. Just I try to decrease the font size. This region is called as active region. And this region is called as, this active region will cover up to this point. Okay, this is actually an active region. This part is called as a cutoff region, and this part is called as saturation region. Okay, this part is called as cutoff region. Cutoff region, and this is saturation region. So these are the 3 regions which it is going to cover in this output characteristics. Clear? So we'll try to discuss about these 3 regions. Okay, this is a saturation region. I think you already have an idea when it is operating under active region, emitter base junction and collector base junction will be, so emitter base junction is forward bias, collector base junction is reverse bias. Okay, when it is operating under the saturation, both are forward bias. When it is operating under the cutoff region, both are reverse bias. So under the active region, what happens if you observe clearly under the active region, see here, when the VCB is increasing, that is when you are increasing the collector base voltage, when you are increasing the collector base voltage, the collector current at one point of emitter current, the collector current is remaining constant. For example, if I'm taking one current as a 4 amperes, okay, if I'm taking one current as a 4 amperes, what happened? At that respect to current, the collector current is remaining constant. It is a completely constant. Okay, for making emitter current as a constant. Okay, so when VCB increasing, this value will also with respect to constant value. So collector current will remain it as a constant with respect to increase in the reverse increase in the collector VCB voltage. But similar, this is, we are going to call it as an active region. So what happens if you are increasing the emitter current? If you are increasing still the emitter current, the collector current is also increasing, because which you already know, we have a relation between collector current and the emitter current, right? What is the relation? Which you already know, the relation is IC is equal to alpha into I, right? I could not be able to write it. So IC is equal to alpha into I, right? So that indicates that which it is approximately equal to. So whenever you are increasing the emitter current, that is input current, automatically the collector current will also increase. Okay, but it is not going to affect with respect to the change in collector base voltage. So this is nothing but an under active region. So this concept will go under active region. Okay. So what happens under the saturation region? Under saturation region, both the emitter base junction and the collector base junction are forward bias. So both are working under the forward bias condition only. So when both are working under the forward bias condition, so what happens? The collector current will drop to zero. Okay. Both are working under the forward bias condition. Just wait. So now, so this is also a forward bias. Now this is also a forward bias. So now both are working under the forward bias condition. So at that time, what happens? The collector current will start decreasing because it will not have that amount of current to flow, because now we have not connected positive terminal here. Now we have connected negative terminal here. Okay, when you have connected negative terminal, what happens? There is no path of collector current because all the electrons will be moved towards this junction, because the negative electrons will be get repelled towards this one, right? So therefore, the collector current will stop decreasing when you are connecting the saturation region. The collector current will start decreasing. Okay, and under the cutoff region, both are going to work under the reverse bias condition. At the further respective time, the collector current is approximately zero. If the collector current is approximately zero, emitter current will be also approximately zero. Okay, so these are the output characteristics of. These are actually the output characteristics of this common base configuration. Okay, we'll try to. Okay, just I'm revising again. We have three regions where the output characteristic is going to drop between the collector current and the collector base voltage. So we have three regions which is going to cover: active region, saturation region, as well as cutoff region. Okay. So with respect to the emitter current, if there is any change in the input current, automatically the output current will also increase, because which it depends, the output current is going to depend on the input current. Okay. But in the saturation region, just because when both are working under the forward bias condition, then automatically there will be no output current, and therefore it is going to drop to zero. You can see very less amount of current, and here also the collector current is also very less under the cutoff region. So next we'll try to discuss about amplification process. See, whatever we have discussed here, the same thing is already available in our class notes. You can see here. See, whatever the points we have discussed here, it is already available in the class notes. See what we have told that, so this thing, okay, we have told that, so to measure this VB, we are connecting one voltmeter. To measure this VCB, we are connecting one voltmeter. You can see, to measure this VBE or VEB, we are connecting one voltmeter. To measure VCB, we are going to connect 1 volt. This is a voltmeter which is connected between emitter terminal and base terminal. This is a voltmeter which is connected between collector terminal and the base terminal. Okay, this indicates the change in the magnitude, change in the voltage, right? So this is emitter current measurement, collector current measurement. This is input current and output current. So whatever the points we have discussed up to now, this will be, all the points are going to cover here. See here. So whenever the VCB is increasing, this characteristics will move to the left hand side. Okay. See here, this is also, okay. In this diagram we have not shown, but there will be three regions in this diagram: active region, saturation region, as well as a cutoff region. Okay, we'll try to, anyway, we are doing this one just because of amplification purpose only. How we are going to do the amplification, we'll try to discuss now. See, just I have removed the DC signal. Okay, now this is an NPN transistor. Just I'm considering this as an input current, this is an output current. Yeah. So just I have removed the DC voltage. Here at the output side, I have a load resistor. Okay, and at input side, I'm giving some AC signal. Okay, at input side, I'm going to give some AC signal, and this value of the AC signal is approximately, I'm considering it as just 5 millivolts. Okay. Just assume this is a 5 millivolts. Okay, and just also assume the input resistance, that is R input resistance, it will be very less ohms at the input side, that is approximately, you can consider it as, so these are the input resistance, and input voltage which you are applying to the NPN transistor to make the voltage amplification. That means you need to get more voltage compared to this 5 millivolts, right? Your target or your required output is how much you are getting this 5 millivolts at the input side. At the output side of RL, it should not be 5 millivolts, it should be more than 5 millivolts. That indicates you are amplifying the voltage, right? So if you want to calculate the current, how much you're going to calculate the value of current, I is equal to V by R. So how much you will get V by R as, just I will try to calculate, I will write the value of II. I think you're going to get 5 millivolts divided by 10, that is 2 into 10 to the power of 3, right? 2 into 10 to the power of 3, we're getting this much amount of current, okay. I is equal to V by R, no? Okay, sorry, it is V by R. 5 millivolts by 5, that is you will get 0.5 milliamperes. Input current you are going to get 0.5 milliamperes because V by R. Okay, V by R, therefore you're going to get input current as a 0.5 milliamperes, right? So you already know that just if you are neglecting the base current, what is output current? Output current is approximately equal to input current itself, right? Output current is approximately equal to input current, which it is equal to how much? 0.5 milliamperes, 0.5 milliamperes. Okay. So how much you are getting input current, you are going to receive most of the 95% of the current, that is equal to 0.5, assuming the amplification factor alpha as 1. We are assuming alpha as 1. If you are assuming alpha amplification factor as 1, therefore you will get I naught is equal to alpha into II, but alpha is equal to 1, therefore you will get 0.5 milliamperes as your output current, which it is same as input current. What is the output resistance? Output resistance is not so much less resistance, it is a so much high resistance. If you consider, you can calculate the input resistance and output resistance from the input characteristics and output characteristics. From this one you can calculate the input resistance, which I have told here, delta VB divided by delta IE. Here also you can able to calculate the output resistance or not, which is equal to delta VCB divided by delta IC. So if you compare the resistance, this resistance is so much high compared to input resistance. Okay, so therefore the RL, the output resistance is approximately of, output resistance will be approximately of, we'll get approximately of 100 kilo ohms. Okay, so the output resistance is approximately of 100 kilo ohms, right? So input resistance is 10 ohms. Okay, but output resistance is approximately of 100 kilo ohms. Therefore, how you are going to find out the output voltage, that is voltage across this point to this point? Okay, just assuming this RL as 100 kilo ohms. So how much you're going to get V naught? V naught, okay, we have only 10 minutes left. So V naught is equal to, so what is V naught? V naught is equal to I naught into R, right? I naught into R means how much you're going to get? 0.5 milliamperes into 100 kilo. So that how much you will get approximately of kilo and milli will be get answer, right? So 100 you will get 50, right? So you will get 50 volts, right? So this is the output voltage. If you see, if you observe clearly how much I have given the input signal I have given only the 5 millivolts. So the amplitude of an input signal is only 5 millivolts, but the output what I am receiving it across the load is 50 volts. So the amplitude is increased so much. There, and you can also say that the input resistance is transferred, the resistance is transferred from input to output. That is, input resistance is very less, that is 10 ohms, and output resistance is very high, that is 100 kilo ohms. Okay, so this is actually the voltage amplification if you are using a speaker, or how the amplifier is going to work. So this is actually one example, so that where it is going to increase the value of output voltage, right? So whatever, if you have a doubts, I have already opened a chat box, you can discuss in the chat box. Okay, because in this class we have discussed about the common base configuration, and in the common base configuration we have discussed about the input and output, and also how you are going to operate for an active region, what we need to consider for input characteristics and also output characteristics. Okay, Then after also we have discussed about the input characteristics, okay, with respect to change in VCB and also the output characteristics. And also the output characteristics for three different regions: active region, cutoff region, as well as the saturation region. And also how we are going to do the voltage amplification, okay, how we can able to increase the voltage from 5 millivolts to 50 volts, okay, by using an NPN transistor or a nothing but an BJT. So this is the today's session. In the tomorrow session we will discuss about the same thing for common emitter configuration. Okay, if you go through the class notes, these are the same points what we have covered. Okay. So if you have any doubts, please indicate in the chat box. If you have any problem, my audio problem or my video problem, any problem, you can discuss here. I think only civil B section are available, right? So for that civil B section. Okay, Hassan, please send me the attendance. Okay, you can raise your hand or anything, and whoever have a doubt, they can raise their hands. I can see. If not, they can ask the doubts so that I can also clear not only you. We can also discuss so that everyone can listen. Right? Hassan, okay, right, done. And okay, right. Thank you all of you. If anyone require, because I have recorded this class, if anyone required the class, from today I will record the class. If anyone requires means, I will send that class. Civilly one person is there. You are not attending for Arvind sir class. Okay, maybe you didn't have that information. Who are there for civil A? I asked the rule number. Civil A only one person. No, Hassan. Civil A actually is dealing by Arvind sir separately. Okay, so civil A is not going to include in our class. Civil A will be have a separate session. I think from 12:40 class. They have already started from today itself. Okay, you can send only the civil B attendance. Okay. Okay. Okay, right. Thank you all of you. Have a good day. Please go through, please try to revise the class. Okay. Thank you. So civil A, and send me the attendance of the civil A one person, Hassan. Okay. Who is that civil A ever? The civil A who is the one person rule number, just inform him or please send his rule number. Hassan, can you say, can you respond? Not, I will mute only you. I asked, he is not telling his rule number. Okay. Okay. Anyway, I will inform to Arvind sir so that I think most of them have not done. Okay, right. Okay. Okay, thank you all of you.